Hi, my name is Eric Samello, and this is my video lab report for Physics 2211 Lab 2, in which I will be examining the motion of a falling object. So some of the main ideas that this lab covers are the concepts that for a falling object, gravity and drag are the only forces in action, and they do not cancel, which means that this unbalanced force is going to result in acceleration in the downward direction due to gravity. This is also reflective of Newton's second law, in which force is equal to an object's mass times its acceleration. Because the forces are unbalanced, then the acceleration in the negative direction will result in an unbalanced force, and the object will accelerate in direction. The formulas relevant to this concept are the velocity update formula and the position update formula, which are both functions of time and an object's force due to gravity, which is its mass times 9.81 meters per second squared, which is the force of gravitational acceleration, and the drag force formula, which is equal to negative b times the instantaneous velocity of an object squared. Some of the key assumptions that I had to have going into this lab is that drag force is always proportional to the square of velocity, which works out in the mathematical calculations that I'll be showing later, and that the force of gravity is constant and equal to negative 9.81 meters per second squared. And below, I have some diagrams showing how the force is due to gravity, the drag force on an object, when the force due to gravity is less than the drag force, then the box's velocity does not equal its terminal velocity, it's actually less. And when the force of gravity and the drag force are equivalent to each other, and then they cancel out, and the box's velocity has reached what is called terminal velocity. Now here I have a video of the motion of the eraser that I dropped. I was unfortunately not able to upload it from Tracker, but as you can see, I dropped the eraser from a height of 1 meter using the point where the meter stick touches the ground as the point of 0, and the eraser is falling in the negative y direction since I used the floor as the x-axis and a line parallel to the meter stick as the y-axis. To construct the computational model, I plugged the formulas that I displayed at the beginning of this slideshow into the starter code that was provided for us so that I'd be able to calculate the values for velocity and force and position. And here's an excerpt from my code. As you can see, the ball weighed about 0.028 kilograms, which is relevant because force incorporates mass into its calculations. The vector and the velocity and position vectors both started at 0, and the size of each time step was about 0.017 seconds. Because this is the computational model without drag force, the proportionality constant equals 0, so it does not factor in air resistance. Here's an excerpt from the rest of my code where you can see how long I use t is less than 0.817 seconds because that's how long it took for the eraser to hit the floor. And in the net force and momentum principles, velocity, position, I just plugged in the values that I needed to in the Python code version of the formulas that I showed at the beginning. And I printed out the y values of position so that I could graph them and calculate velocity from that. Now, for the computational with drag force, for the computational model with drag force, everything else is the same, except I I experimented with numbers until I found a value of b that gave me an n value that was the same as the non-drag force computational model so that I could be certain that the calculations for the eraser had to end up in the same place. And here's the rest of my code for the computational model with drag force. As you can see, this time I incorporated the additional aspect of drag force when trying to find the net force so that I could determine if they canceled out or not. And here are the graphs that I have. The values that I got from the computational values I got from with drag and no drag were extremely similar. And they were also very similar in number to the R squared values I got for each graph, which are close to 0.92 or 0.94. There were some deviations in the starting point and end point for the computational models, for both computational models and the actual experiment, but that could just be attributed to human error, and I didn't calculate the exact starting points correctly. However, as you can see, the computational models with and without drag are so similar that I believe it can be determined that the drag force is almost negligible, and that could probably be because the eraser was so small and it didn't have enough time to fall to maybe reach a terminal velocity, and it had such a small mass and area that it probably wasn't going to factor in significantly into the overall force. To determine which model predicted a terminal velocity, I think it's safe to say that both the with drag and no drag computational models were able to predict a terminal velocity because the the mass of the eraser was so small that it really didn't factor into the overall force at all. And if the object was initially thrown downwards, its initial velocity would have no impact on the object's terminal velocity, because terminal velocity is just the velocity that requires the drag force to equal the net force, and the initial throwing downwards would have no impact on